question before we start? All of you have submitted your project, right?
Yes, okay.
Or final project.
Yes.
Also the presentation as well, eh? Any of you have any problem?
Okay.
I'm still here in Indonesia. Once I'm back, I will give you your test 1 and test 2. Please remind me to hand over your test 1 and test 2. Okay? I will just I will be in my room, but I don't think I will just leave your answering paper outside my door. It's not right. So I will stay in my room and you can come by and get your paper. All right, can we start now? I think there are 35 of us. Please inform your other friends to join. Do you have any question? Ada soalan tak?
Doctor, what topic will cover our...
Oh, it's comprehensive. Okay. It's comprehensive. So all topics will be covered. The final exam is open book. Okay. Only books is allowed. So please, you might want to print the material. And no other notes or whatsoever is allowed. Only your textbook.
So our lecture note is not allowed, right, Doctor?
Not allowed. Sorry. Minta maaf. Okay. Only your textbook. Actually, the notes are based from your textbooks. It's everything there. So you need to refer your textbooks. Any other question?
Last, Doctor, where we can get past year question, Doctor?
Okay, I will share with you the past year questions. But please remind me, okay?
Boleh, Doctor.
Okay, any more questions? Okay, but then we will start with our last lecture, which is on simulation. We have gone through halfway. Is the Monte Carlo simulation. Okay, so I will just glance through the one that we have covered. This is the extension of your queuing theory, simulation. Okay, we talk about Monte Carlo simulation, right? For the simulation, okay, the analog simulation, the use of computer mathematical simulation to analyze the complex system using simulation. Okay, we talk about the simulation is one of the solving the probabilistic problem, right? And it is a kind of a probabilistic model for simulation. And Monte Carlo is a technique used using random number. Okay, it has probability distribution. Okay, and you need to do the random trial using that. This is an example of Carlo simulation. You have, for example, how many demands of personal computer per week. So you have there's no demand per week, one demand per week, two demands, and so on. And what are the frequency for that demand? For example, frequency for one PC per week will be 40% and so on. So from here you can have what we call this the roulette wheel, right, to represent the distribution. 40% one demand, 20% with no demand, 2 PC, 20% and so on. Okay, so you can put this all in one wheel that consists of 100%. Okay, so you can do the rotating. You will spin the wheel, sorry, and then where the wheel stop, that is the number of demand on that particular week. So we talk about this random generator, random number, and what it means by this, and how we are supposed to use this random generator, right? We have to go from one numbers to the other in a sequence manner, right? You can go it downwards or to the right or to the left, as long as in a sequence manner or diagonal as well. Okay, so for example here, for this example, right, zero demand will be from the range of 0 to 19. One demand will be from the range of 20 to 59. This is all based on the distributor. Okay, based on this, right? We have 20, 40, 20, 40%, 20%, and so on. So the accumulation of that will be 20%, plus 0.4 will be 0.6, 0.6 plus 2 will be 0.8, okay, and so on. So you can have that 0 to 19 will be 20%, 20 to 59 will be 40%, 60 to 78 will be 20%, and so on. So you put this based on the cumulative of all the distribution, right? So from here, you can do the spinning or using the random generator. So the first in the list is 39. So 39 means that 39 is in the range of 20 to 56. So R is within this range. 39 is within this range. So R is the demand for R29 will be 1. So the demand of PC is 1. Okay, so you do the same thing for 29 and then followed by 30, 73, 72, 79 until for the in this example you have 15 sequence of 15 weeks. Okay, these are the week 15 weeks. The first week is 39, then followed by 73 and so on. For 49 the demand is 1. For 73 the demand is 2, right? And so on until you have all the 15 weeks. The last one is 69. So if you look at here, 69 is located at range of 60 and 79. So the demand for that particular week is 2. The demand for PC is 2. Okay, so you have the demand for PC is 2. So for 15 weeks, you can add all this together. The numbers of demand for 15 weeks is 31. Okay, for each computer or laptop, the price is 4,300, right? So since you have 23 PCs for 15 weeks, so the total of the revenue for laptop is $133,300. Okay, so from here you can calculate the performance measure, right? So you can estimate the average demand per week will be 31 divided by 15, 2.07 laptop per week. And then the average revenue will be the total revenue divided by 15 weeks will be every week you can have a revenue of 8,886. Okay, so this is how you use the random generator to solve problems using Monte Carlo analysis. All right, and also we talk about the analytic. You can also calculate the demand using analytical or formula, right? you know that the expected value is the summation of all the probability of the demand. So here you have 20%, the demand is 0, 40% the demand is 1, 20% demand is 2, and so on, right? 10% the demand is 3, and then 10% you 4. So if you add all this together, it's a summation of the estimated demand for the summation of all this, right? Time the probability. So means that it is estimated that based on the formula, it's 1.5 PC per week. So you can see here the difference is over here you have 2.07, but using analytical or using formula, just 1.5 PC per week. The question is why there's a difference here. Okay, anybody can answer? We talked about this before. Why there's a difference using mathematics or equations as compared to using Monte Carlo analysis? Why the average demand is different? We have 2.07 at laptop and we have 1.5 for the using equations. Lagi tak perbeza? Kenapa? What happened actually here?
Data size.
Yes, the size. Why the size matters?
The more of the size is more accurate.
Okay, the more the number, the more samples that you have. Over here you have only 15, right? So the more numbers of samples you have, the more accurate. Not to say accurate. Once you have all, you are covering almost all the probability, yeah? Almost 100%. Right? Then it will come to close to 1.5. The more data you take, the more it will be closer to your mathematical equations. Okay? Very good. Right? This is what is it. The more period that we have, the more accurate. And the more sample that you have, the more accurate. And then again, simulation will not reach, it's not equal to the analytical system unless you have enough trial. You have many samples. Once you have many samples, it will reach steady states. Okay? And it is sometimes quite difficult to validate the simulation. So there's a process of how to validate the simulation, which is based on your random generator. Okay, where you're supposed to study in your simulation class for validation and verification. Okay, you can validate using random generator, and you can verify using the mimicking. Does it mimic the real situation or not? We have to use the extreme value for mimicking, or you can ask the experts whether it mimics the real situation or not. Or you put extreme value, for example, you put big number, or you put very small number, 0, for example. Look at whether it falls into the correct manners or situations or behavior. Right? This number, we call it random number, how the random number can be generated. Okay? It gets more complex. The simulation model gets more complex, and it becomes impossible to perform manually. Because of that, we use the mathematical process for generating random number, and this is called the pseudo-random number. Okay, these are the characteristics of pseudo-random number. Okay, or artificial random number. Okay? Must be uniformly distributed. The numbers must be uniformly distributed. I share with you how people come up with this. Sorry, how the computers come up with this number, which is through a lot of, for example, addition, subtraction, division, multiplications, okay, and put some powers on that until it becomes so random. It is called uniformly distributed, right? And then the techniques must be efficient enough, and the sequence of random shouldn't be reflect patterns, shouldn't reflect patterns. So we share with you how to generate this, right, from the Excel, right? So you can see here it is not uniform. You cannot see any patterns in here. So this is the behavior of random generator. Okay. Now this is a new one. We haven't discussed yet. Okay, this is one of the example. This is a Willingham mills. In this mills, actually, they are producing yarn, benang, benang. And this yarn, the arrival comes under in batches. Benang ni come in batches, alright? And arrival rate in batches is, for example, 1 day or 2 days or 3 days or 4 days. Okay. For arrival rate of 1 day, the probability is 20%. The arrival, interval arrival, 2 days, interval arrival, rate of arrival, 2 days will be 40%, 3 days will be 30%. The yarn that arrive 4 days, in 4 days interval, arrival is 10%. Faham tak? So the yarn, benang ni, a batch of yarn, a batch of benang, okay, banyak, will come in 1 day will be 20%, or in 2 days, the arrival, the arrival interval in 2 days will be 40%, 3 days will be 30%, and 4 days will be 10%. Say from here, you can put you can see you can have the random number for arrival 1 will be between 1 to 20 based on the probability. Okay, so the cumulative probability will be here 2.2, 0.6, 0.2 plus 0.4, 0.6, 0.6 plus 0.3, 0.9, 0.9 plus 0.1, 1. So the range for 1 arrival, okay, would be 1 to 20. For 2 would be 21 to 60. For 3 would be 61 to 90. And for 4 would be 91 to 99. And including here is 0. If you have 0, if your random generator shows 0, it means that the arrival rate will be 4 days. Okay. So when this yarn comes into the process, right, it will take 5.5 days, half a day. Okay, it can take half a day to be processed at the processing area. Okay, or it will take 1 day, or it will take 2 days. So this is the service time. So here you have the arrival, inter-arrival rate, and this is here the service time. Okay, arrival interval, and also service time. This is where the yarn arrives, and over here how long it takes for it to be served. Okay, so it could be half a day, or 1 day, or 2 days, depends. So if 1 day, then probability here is 20%, half a day. 1 day is 50%, and 2 days is 30%. So over here again, you can put your random generator, the random number, okay, based on the probability. So you have 0.2 between 1 to 20, and then 0.2 plus 0.5 will be 0.7. So here will be 21 to 70, and after that 0.7 plus 0.3 will be 1. So the next range will be from 71 until 99, and 0 as well. Okay. So this will be your random range for arrival. This is queuing system. You arrive, you be served. Okay, you arrive, the yarn arrive, and then being served. Right. So you can do let's say you have 10 batches, 10 batches. So this will be the first batch, right? The first batch, definitely for the first batch, just started, your arrival clock is 0, right? Okay, and the service time also 0. Okay, for the first one. So if 0, then you have to look at the service time when the time the first one from the generator is 65. So this is based on this one, based on the generators. 65, where is 65? 65, I think this is the one, 65. So you look at the here, in 65, this is 71, 12, this is for arrival, 71, 12, 48 and all that. And for service, you have 65, 18, 17. Sixty-five, 71, 18, 12. Betul tak? This is the one, 65, 71, 18, 12, 17. So in this problem, they took second column as the sequence, starting from 65, followed by 71, 18, 12, 17. $65 over here, 71, 18, 12, 17. Can you see that? Nampak tak? Can you see the sequence here? Are you with me?
Yes. Okay.
Yes. All of you see the sequence? The first one is 65. The second one is 71. The third, let me use the, it is the first one, 65, right? Followed by 71, and then 18, and then 12, and then 17, then 48, and then 69. Okay, this is based on the second column of the generator, random number generator. 65, 71, 18, 12, 17, okay, 48, 89, and so on. Until over here we have 10 batches. Until you have all the 10 batches. Okay, so first there'll be no arrival, but then the service time is there. So the first one is 65, 65. If based on the range, this is having only one day of processing time, service time. So the departure clock is 1, right? Then the next one is the first batch. The arrival is 71. 71 is located at range 3. If you look at here, 71 is here. 71 is 3 days. Okay, the arrival interval is 3 days. Okay, over here 3 days, right? Then we have 3 days arrival clock, and then the enter physical clock is 3 days, right? And then once you arrive, then the yarn will be processed. How long it takes to process? Then the next sequence will be after 71 is 18. So 18 is the service. So here's the service. 18 is here, which is between 1 to 20, meaning the service time for this batch of yarn is 1.5 day, 0.5. This is 0.5. So the accumulation of this is what? 1 plus, so you have three days here, plus another half a day, so 3.5. So the departure clock here is 3.5. 3 plus 0.5 to 3.5. Okay, and then after that, 12 from the random generator is 12. 12 meaning that the arrival interval is 1. So the arrival clock will be 4. 3 plus 1 is 4. So the the enter facility clock is 4, right? And then after that, this batch will go into the process, and the process will take the random of 17, which is between 0 to 20, which is 0.5, again 0.5. So 4 plus 0.5 will be 4.5 here. Okay, so you do all this from batch 1 until batch 10, right? So at the end, you can calculate the waiting time. There's no waiting here because arrival clock is 0. There'll be no waiting here. There's no waiting here. There's no waiting here. This is also no waiting, but over here you have 1 day waiting, meaning the arrival is 7, but you cannot enter because the process, the 7 finish. Okay, so you have to wait. There's a queue here. So Q is one time. The time is, for example, 1 day. Okay. The same goes for the rest. You can see the queue. Queue for 2 days. Then this is another 3 days and so on. So this become the waiting time. Okay. We can use formula, right, to calculate the waiting time. But over here we use simulation. Simulation because we have the distribution. Okay, over here you have 12.5, the waiting time. But then over here you have the time in the system. This is the time in the system, right? Until all the 10 batches, the time in the system for all the 10 batches will be 24.5. You add all the time in the system. So from here you can have the performance measure. So it could be the average waiting time, which is 12.5 divided by 10 batches. It's 1.25 batch. 1.25 days per batch. Okay, that would be the average waiting time. And then you have the average time in the system, which is 24.5 divided by 10, will be 2.45 days per batch. So this is how you use queuing theories problem using Monte Carlo analysis or simulation based on Monte Carlo. Any questions so far? Is that clear? Ada soalan tak?
Clear, Doctor.
Okay. If ada soalan, please ask the question. Or else you the final exam, these are one of the potential problem. Okay, this is another. This is the company, the same problem. The building terminals, right? The result may be viewed by skepticism. Why? Why this is skepticism? Kenapa? It's only 10 batches. So the numbers of samples is too small. So that's why it's quite skeptic. So it doesn't ensure steady state result. So you need to have more data to ensure steady state. And then the starting condition also can affect simulation result. Over here you start at 0. So the starting, that's why for simulation you have to do the run setup or running time, run up. So you have to have the run up first. Okay, warm up first. You have to warm up before you can start to collect the data. So the starting condition, it can affect the result. Okay. So here, if there's no batch in the system at the start, then the simulation must run until it replicates normal operating time. So you have to do several times. And because over here you say that the batch at the start there's no batch, but because you have the start and the start time for the simulation for a long time, then this start time is no longer 0. Okay, meaning you have to take after you remove the start time. Okay, so if the system start with item already in the system, the simulation must begin with item in the systems. So we have to. Okay, you can use the simulation, the software to do the simulation, the Monte Carlo simulation. All right. Sometimes, or not most of the time, you have a continuous function. where you have continuous distribution. Over here is a normal distribution. This is not continuous. Okay, you can see here the distribution is 0.2, 0.6, the normal distribution. Okay, but sometimes you can plot this into a form of equations, and you can make a continuous distribution. Okay, not discrete distribution. For example, here, okay, this function here, we have the function which is equals to f of x equal to x over 8, and this x is between 0 to 4 minutes. Okay, and this is a function. Okay, so you can have the cumulative distribution for this is the integration. You have the integration between 0 to x, and then from here you can calculate the integration, which is 1 over 8 times 1 over 2 x to the power of 2. Okay, this is the integration between 0 to x. So over here x is 4, so it is from 0 to 4, right? Okay, so here you can get f of x is equal to x squared over 16. Okay, so this is the cumulative probability for x. This is the function. The cumulative velocity will be x squared over 16. Okay, which is the integration of this function. Okay, so assume that f of x is the random number r. Right? So r is equal to x squared over 16. R is the random, because this is the distribution, f of x distribution. We assume that this is the random number. Okay, so we change the distribution to r. R is equal to x squared over 16. So from here you can calculate x. What is x? X is 4, the square root of r. Okay, can you see that? So you just this integration of x squared over 16 equal to r. X is equal to what? 16. X squared is over 16. So x is equal to 4 square root of r. Then now r becomes this is the random number. So by integrating this random number r, okay, so we can calculate the value of x, which is the time. So by knowing the random number r, okay, times 4, we can identify the value of time, which is x. Okay. So for example, if r is equals to 0.25, then x is equal to 4 times square root of 0.25, which is 2 minutes. Okay. So this r is the random number. Okay. So this is how we make use of, or how can we use the continuous function to identify or to find the value, a certain measure based on this distribution, continuous distribution. Okay, let us look at an example here. Okay, this is a Piccolo manufacturing company. They have to decide whether to implement the maintenance program. If they want to implement the maintenance machine program, then the cost is 20,000 per year. But then it will reduce the frequency of breakdown. Okay, if they apply the maintenance program, whereby they have to pay the cost of 20,000, it will reduce the frequency of breakdown. Okay, and assume that the repair is 2,000 per day. Okay, for every breakdown, 2,000 per day for the repair, the cost of repair. And over here, we have for the machines, since this is machine, the machine breakdown is time between machine breakdown is following the continuous probability distribution, which is example here, the probability distribution for time between machines breakdown will be equals to x divided by 8, okay, which is equal the same as we have here, x over 8, right? So this is the frequency of the probability of time between machine breakdown. Okay, where X is between 0 to 4. Okay, the frequency of the machine, that time between machine breakdown is between 0 week to 4 weeks. Okay, could be 0, could be 1 machines, right? Time to machine breakdown. Every 1 week, or every 2 weeks, or every 3 weeks, or every 4 weeks. Okay, so this is based on continuous, right? So from here you can calculate the X. Okay, X is the time, which is 4 square root of R, the one that we have calculated here. X is equals 4 to the power 4 square root of R. So here you can have the value of R, right? So now the random here will be R, Ri is the random. You need to identify the value of R. Okay, so we know that and also given the machine repair time. Okay, this is the time between machine breakdown, right? Which is based on continuous distribution. But then we know that from here, the repair time will take 1 day, okay, or 2 days, or 3 days. This is the repair time. Okay, every time when the machine breakdown, could be after 2 weeks or after 3 weeks, right? And it will take 1 day, or 2 days, or 3 days. 1 day, the probability of repair time 1 day is 15%. The probability of two days will be 55% and 30% for 3 days. Okay, and from here you can have the range of R, which is R2. So you have R1. R1 is the time for breakdown, and R2 is the times that the repairing time. Okay, so range for the first only 1 day will be from 0 to 0.15, or from 0 to 15, right? Or from 16 to 70, and 71 to 100. Okay, so this will be the random range for R2. Okay, so now you have one is R in equations, right? So you need to identify the value of R in the equations, R1, R2, R3, Ri, to find the value of X, which is the weeks between machine breakdown. How many weeks between machine breakdown? Okay, and we have also the range for machine repair time, how many days. Okay, so again, the revised probability time between machines, which is this equation, and for this one, it was stated in the problem here. Okay, it was taken between 0 to 6 days. So f of x is equal to x over 16. This is the revised one. Okay, this is the current situation. Okay, this is without the maintenance. Okay, so now you have the implement the maintenance program with a cost of 20,000. Okay, because of this, okay, your probability is being revised, right? So this is the time between machines with maintenance program will be between 0 to 6 weeks. Okay, so the weeks between machines breakdown is 0 to 6 weeks. Okay, and then from here you can get the equation, which is x is equals to 6 square root of Ri. Okay, just now we have 4 square root of Ri, right? But this one, sorry, R1. This one is 6 to the square of R1. Okay, and then the repair time, you have the new repair time here based on this new policy by having the maintenance program. So 1 day is 40%, 2 days is 50%, 3 days is 10%. So this will be your range for R2. Okay. Right, from here you can do the calculation. Okay, this is the simulation without the maintenance program, where you have this first this one, and also this table. Okay, this equation here and also this table, right? And this one, this table is for having maintenance breakdown, and the equation here is having the maintenance program. Okay, and this the repair time for having the maintenance program. So over here, you do the simulation without maintenance program, right? So breakdown one, which is we look at the R1 based on the random generator 0.45, and then the breakdown this is 0.45 from the random generator. So you use the equation. Equation is what? 4 square root of 0.41, which is 2.68. This is from the equation. 4 times square root of 0.45, which is 2.68. Okay, and then you, after a breakdown, then it have to be maintained, right? It takes how many days? Which is R2. The first R is 0.45. The second R is 0.19. Okay, look at the table here. Just now? Again. What's the first one? It's 0.45 and then 0.19. 0.45, 0.19, and then 0.90. 0.45, 0.45, and 0.19. Let me see where is it. Okay, here. 0.45, right? And then 0.19 over here. And then 0.90. And then 0.69. Can you see it? Nampak tak? Can you see the sequence?
Can.
Start from 0.45, followed by 0.19, and then 0.90, and then 0.69. Okay. Point 45, 0.19, 0.90, 0.65, and so on, right? So all these value here are taken from the random number generator. Okay, so from here you have all for 20 breakdowns. For 20 breakdowns, what will happen to the situation here? Okay, so from here you know the cost, right? The cost for repairing. If 2 days mean for every day you have to pay for 2,000. So here 4,000, 4,000, 4,000, 6,000, 3 times 2,000, 6,000 until all of it. So meanings that you have you need to spend 84,000. Okay, the cost of without maintenance is 84,000. Okay, this is without maintenance. Now you have with maintenance. With maintenance, the formula for breakdown is 8 square root of R1, sorry. R1, 8 square root of R1, 0.4. So 8 times 0.4, square root of 0.4, which is 4.03. Okay. The same, this one you use the same random generator, 0.4, 0.45, this is 45, 19, 90, 65, 84, 51, and the same. But here you take only 14 breakdowns, right? In this equation or in this problem, okay, you're taken only 14. Over here you take 20, yeah? So this is for 14 breakdowns, right? The total for 14 breakdown is 42,000. 42,000. This is the average. You add all this, and this is what happened for 18. for 14 breakdowns is 42,000. Okay, the cost of breakdown. All right. So, implement of the maintenance program, since the cost APA is 40,000, right? But the maintenance program is 20,000, right? So, implementation of maintenance programs, the cost saving appear to be 42,000. Where do you get this 42,000? Is 84,000. This is the cost of without maintenance program minus 42,000. Okay. This is the cost of this is annual. The total annual repair cost is 40,000 total out. Total. So you have 84 minus 42 will be 84. Sorry, 48. 48. Okay. So the maintenance program is 20,000. So actually you have to save the money, which is around 22,000. Okay. So you can save by having the maintenance program, you save around 22,000. Is that clear?
Yes, betul.
So the conclusion here of some of the remarks that you need to have, you need to know that there are potential problems caused by simulating both systems only once. If you do the simulation only once, then there's potential problems. Okay? The result exhibits significant variations since the time between breakdown and repair are probabilistic. This is uncertain. So you have some variation here, right? So to be sure you have a better answer, okay, you need to run more times, more numbers of samples to be taken. You have to run it many times, you have better average. Okay. So for having computer simulation, you need to have more times or more samples, so you can have better results. Okay. So the outcomes of simulation modeling are statistically measured using average. Typically subjected to additional statistical analysis. You need some, because to have the performance measure, you might use some statistical analysis instead of just a very simple one. And also you need to have some form of confidence limit to develop since it is a sort of variation, a lot of variation, so you need to have some form of confidence limit. Okay? Usually you have 90% or 95% confidence. Okay, so this is an example of confidence limit, plus minus 95%, lower and up. So this is you use this confidence limit as well for the analysis of your results. Okay, so many realistic simulation problems contain more complex distribution. So because of that, you have what calls a lot of packages or models or simulation software. One of this is Crystal Ball. Crystal Ball is a software published by Dimensioning. Crystal Ball, but we don't have Crystal Ball here. So we have, I can share with you, you learn Witness, right? This Witness also a simulation software. So you use this simulation software, okay? So you are very familiar with Witness, but let me share with you one of the tools or the software, I think, which is very powerful, and I think which is FlexSim, and Mr. David already make a demonstration for the software. Okay, Ya, saya tunjukkan software. The one that have shown that Mr. David share with you. Right? You can download this software. It's for free for usage. But let me share with you the one of the video of this software. If you can download the software and try use this software for your project. Very simple. Let me share with you the video. Welcome to the world's best simulation model. All right. If you have problem, you just press out. This is the software. This like sim. Can you see the video, Pada?
Yes, doctor.
This is the flight sim. It's very systematic way of explaining how to use this software. So you can use this video. I will share with you the link later.
Welcome to FlexSim, the world's best 3D simulation modeling and analysis software. FlexSim lets you take the things you know about a system, plus the things you can assume about the system, and translate those into a digital model where you can learn, experiment, and optimize the whole system. Today, you're going to build your very first FlexSim model. If you haven't already, sign up for a free FlexSim account to download and install the latest version of the FlexSim software. Before we begin, if you have a license but haven't activated it yet, please do so now. There's a link on how to do this in the description. If not, no problem. You'll still be able to build this model using the free Express feature set. From the start page, create a new model and you'll see a pop-up where you can set the model units. Let's use the defaults. The middle pane is the model view, where you will build the digital model of your system to scale and entirely in 3 dimensions. To the left is the 3D object library, which has many reusable, pre-configured components that you can use for fast and simple model building. Using your mouse, left-click and hold while dragging out a source object, and then release left-click to drop it in the model view. You just added a fixed resource object. These objects send and receive flow items, the physical components that flow through the system. This specific object, the source, creates flow items. Now that you have an object in view, we have a point of reference to look around the model view. If you hold left-click on any empty space in the model view and move your mouse, you can pan the view. Hold right-click to rotate the view and use the mouse's scroll wheel to zoom in and out. If you're lost and want to recenter the view, just right-click on an empty space, hover over View, and select Reset View. There's another way to add objects to the model. Double-click with the left mouse button on any empty space in the model view to bring up a quick library, and choose the Queue object, which is right next to the source. Flow items will spend most of their time doing one of 3 things: being transported, being processed, or queuing for their next event. This queue is another fixed resource, and flow items from the source will queue up here before being sent downstream. Let's add 2 more objects from the library, a processor and a sink. These are enough objects for a basic model, but they won't do anything until we create relationships between them. We do this with object port connections, which define possible flow item routes to and from fixed resources. The most common connection involves inputs and outputs. To make this connection, hold the A key to enter Connect Objects mode, then click the source and then the queue to connect them. In Connect Objects mode, you can keep clicking to connect one object to the next, in the direction that items will flow, or you can quickly release the A key and then press and hold it again to reset things and connect two new objects together. You can now see a visual indicator of the connection, with an outward pointing red arrow showing the output port on the source, an inward pointing red arrow showing the input port on the queue, and a black line between them. There's another way to connect objects. Left-click the queue and notice the white arrow just outside of the manipulation handles. Left-click and drag from that arrow to the processor to connect them. Choose your preferred connection method and finish up by connecting the processor to the sink. One final thing before we run this simulation. For this example, we're building a model of a product testing system, and we need to have the right inputs to represent the system's behavior. Based on quick real-world observations, products arrive for testing on average every 15 seconds, but there are also some outliers with 60 seconds or more between arrivals. The exponential probability distribution is Flexsim's default for these inter-arrival times, so we just need to edit the default value in the source. If you left-click on the source object, its properties will show up in the right pane, where you will find properties for most of Flexsim's tools and objects. In the source area, and under the inter-arrival time field, you'll see an expression for the default exponential distribution. Click the Edit Parameters button to bring up the distribution parameters, and change the scale to 15, then click away from the pop-up to save your edits. We also have some observations for our processor, which represents our testing station. Left-click on the processor to bring up its properties, and then find the process time field in the processor area. The default value is a static number, so click the black arrow to the right of the field, hover over Statistical Distribution, and choose Triangular. This distribution wants 3 parameters: the minimum time testing will take, which is 8 seconds, the maximum time it will take, which is 30 seconds, and the testing time we observed most often, which is 15 seconds. While you're here, let's rename this processor to Testing Station using the naming field at the top of the Properties pane. This model is actually ready to run. Just above the Library and Model view, you'll find the Simulation control bar. It's good practice to always press the Reset button to get everything to its starting state, and then press the Run button to run the simulation. It might take a few seconds for the source to add our first flow item to the system. Press the Skip button to skip to the next simulation event, where our box passes right through the queue and into the processor, and then leaves the model through the sink after processing. You'll notice a few things in our model. We're using statistical distributions, or stochastics, instead of fixed numbers for things like arrival rate in the source or processing time in the processor. Using random numbers adds, well, randomness to the model, since just like in the real world, there's often variability in how long things take. Simulation lets you capture this complexity in a way spreadsheets can't. If you use the run speed slider to increase the simulation run speed, you'll see the flow item queue grow and shrink over time, all thanks to variability. The second thing you'll notice is that the flow items teleport from object to object. Press the Stop button in the simulation control bar, and let's introduce the Task Executor. Task executors are mobile resources that perform tasks, like transporting flow items between objects. Add an operator to your model. The operator will need to be connected to our system, but we're going to use another connection type to do it. When you left-click the operator, you'll see a white square just under its manipulation handles. Click and drag between this square and the queue to make a center port connection, a reference connection we'll use to transport flow items between the queue and the testing station. You can also use the S hotkey to enter center port connections mode. Unlike the regular object connections we did earlier, where the connection order matters for defining item flow, center port connections are for reference only, and connection order doesn't matter. Now we need to make use of this reference connection. Click the queue and find the output area in its properties. Click to check the box for Use Transport, and a few new options will appear. By default, Use Transport will look to use the first object connected via a center port. In this case, The first and only center port connection is our operator. Reset and run the model again to verify that the operator is now loading flow items at the queue, transporting them to the testing station, and then unloading them to begin processing. There you go, a simple digital model of a small product testing system. Now it's time to gather some data from it. Let's add some charts and graphs to see what's happening here. In the toolbar, click Dashboards and Add Blank Dashboard to open a new dashboard in a split pane between the model view and properties. The context-sensitive library has now been updated to show all our pre-built charts. First, let's drag a state chart into the dashboard. It's blank right now, so let's click on it to bring up its properties and find the Objects area where we can add objects to be displayed in this chart. The easiest way is using the sampler, which is the eyedropper icon. Click once to enter sample mode, and click again on the testing station to add it to the chart. This will show us how the testing station is utilized during the simulation run. Drag out another state chart and this time sample the operator so we can see how they are utilized. Finally, drag out an average content chart and sample the queue so we can see the average size or content of the queue. Reset and run the model and speed things up so we can see some data. The testing station is well utilized, but the average content in the queue just keeps going up and up. How could we keep the queue from backing up so much? Would it help if we added some more testing stations to the model? First, let's make the number of testing stations an editable parameter in our model so we can quickly adjust the number. Click the Toolbox tab in the left pane and double-click Parameters to open the default Model Parameter table. The table will open as a new tab in the Model View pane, so let's move it to a more convenient location. Click and drag the tab of the Parameters table around the FlexSim window to see the window docking options you have. Let's dock it to the lower half of the Model View pane. There is already a default parameter, so let's change its name to Testing Stations. Now click the Value cell and then the black arrow button to show its parameters. We want to test how our model performs with a different number of testing stations, up to 5. Change the type to integer and make a lower bound of 1 and an upper bound of 5. Now we need to make a reference for this value. Click the sampler, click the queue in the model view, and then choose Delete and Copy Out Objects. Since the testing station is the only output object of the queue, this will now add and remove these objects as we change its value. Let's give it a try. Change the value to 5 and click the Reset button. All 5 of the testing stations were added to the same location, and you can tell by the additional connections showing up. This is fine for our model because travel distance isn't a factor in our study. But if it were, we'd want to do something slightly different to spread these objects out. Now click Reset and run the simulation again. The additional stations give us the capacity to process up to 5 flow items at the same time, and you can see in the dashboard that our queue is hardly backed up at all. You'll also notice that the additional testing stations have been automatically added to the state chart, and some of these stations are utilized quite a bit more than others. One station was too few, but 5 looks like too many. What's the right amount? Let's do an experiment. If you're using FlexSim under a free Express feature set, you won't have access to the tools we're about to use to analyze this model. If you'd like to try these features for yourself, contact your local FlexSim representative, tell us about the work you're doing, and let's talk about an evaluation license. First, a little prep work. Double-click Performance Measures in the toolbox and move this table inside the same pane as parameters. Use the up arrow to add a few more performance measures for a total of 3. What are the key performance indicators for our project? The first one is testing station utilization, so change the name in the first row to reflect this. For its value, sample the testing station's state chart, hover over utilization, and choose Utilization Average. This will return an average utilization across all active testing stations. The second measure will be operator utilization, so rename the second row and sample Utilization Average from the operator's state chart. Finally, we want to keep a close eye on the queue's average content. Rename the third row, Sample the Average Content chart, hover over Average WIP, or Work in Progress, and choose Average WIP Average. If you reset and run the simulation now, you'll see these performance measures update as the model runs. And now we're ready to test some scenarios. In the menu bar at the very top of the FlexSim window, click Statistics and then Experimenter to bring up the Simulation Experiment control window. This is FlexSim's Scenario Manager. Model parameters are the drivers for different scenarios, and ours is already set up. Expand the Parameters option and check the Testing Stations box, and this parameter will be added to the list of scenarios on the right. Click the green plus button to add 4 more scenarios and change their values to 1, 2, 3, 4, and 5. You probably guessed that each scenario will evaluate a different number of testing stations in our model. Now click the Experiment Run tab. This is where we'll set up how our simulation replications will run for this experiment. Let's update the number of replications per scenario to 25 so we can get a large enough sample size for more valid results. And each replication will use different random numbers, so the results for each one will be a little different. For runtime, change seconds in the drop-down menu to hours, and change the runtime value to 8. We want to see a full day of data for each replication. Now click Run Experiment, and FlexSim will get to work. Each bar segment represents a replication, where an entire 8-hour period is simulated. FlexSim's experimenter is multi-threaded, so it will run a replication on each CPU core simultaneously. When a replication is finished, that segment will turn green, and the experiment is finished when everything shows up green. Click View Results, and let's see what happened. The first thing you'll see is a chart of all the replications we did for each scenario, each with box and whisker plots. This is testing station utilization, and you'll notice that Scenario 1, with just a single testing station, had the highest average utilization at just over 80%. There are significant decreases in utilization in both Scenarios 2 and 3 before tapering off in Scenarios 4 and 5. Click the drop-down for testing station utilization to choose a different performance measure, operator utilization. Here, we see an immediate improvement in utilization with Scenario 2 and no further improvement with the other scenarios. Finally, the average queue content measure also shows Scenario 2 with a clear improvement to a near zero average queue size. Based on the data, Scenario 2 looks like a clear winner. And if you want to dive deeper into the results, you can click Replications Plot and choose something like Scenario Comparison to check for statistical significance, or generate a report to evaluate the data in a different program. Congratulations on building and analyzing your first FlexSim model. If you'd like to continue your simulation journey, we have many free resources available to you, including video tutorials, Q&A entries, documentation, and much more. Check out the links in the description to keep exploring. And we hope you'll get in touch with us soon. We'd love to hear about your next project.
Okay, that is about the software. To use witness, right? But the witness that we have in UTM is a very old. Doesn't have the latest features, right? But this one, you can make use of the simulation, the student's version or the trial version. You can run your project simulation if you want. And this is actually not only it is 3D as well. Right? It's the 3D, and also you can use artificial intelligence. It has some artificial intelligence in it, and also you can use virtual reality. Yeah? You can go walk inside, or you can have the feeling of immersed into the problems. Okay, so these are the beauty of FlexSim so you can make use of this. We're going to buy this letter in our next year or the next year. We'll try to get it this year. Okay, you can try this. It explains quite detailed. So you can download this the software from the webs. I will share with you the link later. I think that's all about simulation. Do you have any question?
Doctor,
Any question? Yes.
I want to ask, for the final exam, is it going to be closed book or open book?
It is. I will be there during the exam, so you're going to be open book.
So,
Doctor, can you consider back the slides?
No, I can't, because there's a lot of problem with occur. Because once it's an open book, and then if we have a slide as well, then there will be question. Open book is good enough. Before this, we don't have open book.
so we can only bring our textbook to the final exam.
Yeah, you can bring your notes. I mean, the printed textbook. You can print it
Thank you, Doctor.
for the purpose of study. Yeah, it's okay.
Doctor, for the
Yeah,
syntax calculations, do we need to prepare for it for the final test, or it will
For the what? For the what?
syntax method?
For the syntax of the
Syntax, yes.
for the syntax measure. What's your question again?
It will be
Sorry?
included in final?
The final is comprehensive, yes. I'm not so sure it's going to be included, but the problem is comprehensive. You just make sure that all the learning outcomes, the topics that covered in the syllabus, you should make sure you know how to do it.
Yes, Doctor.
Refer back to your syllabus. Okay, the one that is not in the syllabus will not be off in the final exam. Only the one that already covered in class and also in the syllabus. I think I've covered all in the syllabus. That answer your question, Mami?
Yes, Doctor. Thank you.
Welcome. Any other question?
Doktor buat tips lah.
Apa dia?
Ada tips lah untuk final.
Oh, I will give the hints. Please remind me to give the hints. The hints will only be given a day before the final. So you cannot use the hint, only the hint for the preparation for your final. You have to prepare from now. The hint is only for a sort of safety net for you. But please don't depend only waiting for the hint. But to help you a bit, I will give you the hints, but only will be given a day before the final.
Can we make it 2 days before final, Doktor? Because
Boleh je, Fikri. Sebab apa hint is
presentation, Doktor.
consider you tak belajar betul-betul. The purpose of our learning is about knowledge. I want you to have as much knowledge as possible. If I give you the hint, you will keep studying the rest of the whatever you need to know in this course. That's why I will not do that. The hint is only for you to have the last revision, not the initial revision. Okay, you have to study from now. Not from now, from before.
Okay, Doktor.
Okay, that's the purpose, Fikri. Okay. Ada lagi soalan? Okay, I will be back on the 4th. Okay, if you have any more question, I will be in my office. Okay, until the 7th. Inshallah. So hopefully by then all your course work marks will be given, will be provided. Ada soalan lagi tak? Yes, no? Okay, let me open the attendance list. So this is for section 27. Okay, is the okay, this is for section 20, section berapa? 7. Can you please scan your attendance? Section 7. By the way, for your project, if you can come up with the simulation, okay, you use simulation will be an added advantage for your project. But so you already submitted, no problem. You already submitted, right? Okay, just learn how to use it. Any more students from section 7? We have 16 here. Ada lagi tak? Ada any more students from section 7? Tak ada, I will stop sharing. This is for section 27. Okay, section 27.